Hey everyone, welcome back to Calculus 1. This will be part A of lecture 3. And in this section, we're going to continue with our investigation of limits. And specifically, we're going to introduce a range of theorems that will allow us to evaluate most limits that you encounter as part of this class. Now, there'll be always some limits that are outside of the range of theorems that we're going to investigate, but this will get you very, very far. Most of the things that we encounter in the everyday world will be kind of handled by the theorems that we introduced today. So let's go ahead and jump into it. We'll call this section 1.3, evaluating limits analytically. Okay. And so we want to start with a couple of theorems that are very, very important, very powerful, and kind of teach us how to deal with your basic functions and the limits of those functions. And so the first one says, let B and C be real numbers and let n be a positive integer. Then these three very simple limits are covered by this theorem. So the limit as x approaches c of a constant function b is just equal to the value of the constant function. The limit as x approaches c of the identity function x is just equal to c. Right? Remember, the identity function is just the straight line. And then the limit as x approaches c of x raised to the nth power is just c raised to the nth power. Now here, remember, n is a positive integer, so this is not x to the 1/2 power or x to the 3.76 power or anything like that. This is x to the first power, second power, third power, fourth power, positive integers. Theorems like this and a lot of the theorems that we run into in this section can be proven relatively easily using the epsilon delta definition of a limit. We won't prove most of the stuff that we talk about today. And in fact, throughout the class, proofs are not really the focus, but we will prove this one. We'll prove item 2 here, just because it just gives you some sense for how these things can be shown using epsilon delta definition. Right, so this one is very simple. It's 4 lines. First step, let's let epsilon greater than 0 be given. So you give me an arbitrary length, and I will choose a delta. The delta I'm going to choose is just going to be the same as your epsilon. You give me an epsilon, I'm going to say, okay, I'm going to let my delta be that. All right, then it's pretty trivial to see that if x is within delta of the limit point c, then f of x minus L. Now remember what this is, the identity function. So f of x is just x, and L is just c. So f of x minus L is just x minus c. And if we assume that x minus c is less than delta, then x minus c is less than delta, and delta was set equal to epsilon. Right, so we can get our the distance between the function and the limit less than epsilon by just making delta equal to epsilon. So they don't get much simpler than that. Okay. Let's talk through a couple of examples of this first theorem. Okay, and this is just to make it concrete. The first one says the limit as x approaches 2 of the function f of x equals 3 is just 3. Right? Straightforward, right? Because it's just a constant function. It's equal to 3 no matter what x is. Okay, so that one's easy. The limit as x approaches -2 of x, f of x is equal to x, is equal to -2, right? So just plug that value in, and so we can see that that's the case here. And then finally, the limit as x approaches 2 of x squared is equal to 2 squared, right? So you just plug in the limit point, and you get the limit. Okay, and so here's what that looks like. It's a nice, smooth quadratic function, no holes, nothing to worry about. You just, as you approach 2, the value of the function approaches 4, and there you go. Okay, so 3 simple examples of the first theorem. Now, the first theorem may not seem all that powerful, right? It's just like, okay, a constant function, identity function, and x to the n. But when you combine it with our second theorem here, you'll see that there is a lot. It is quite powerful, actually. And so this theorem says, let's let b and c be real numbers, right? So these are taken to be constants, real numbers. And let's let n be a positive integer again. Okay, so then I've got two functions, f and g. They're both functions with limits, right? So the limit of f, the limit as x approaches c of f of x is equal to L. And the limit as x approaches c of g of x is equal to k. So I've got these two functions that have limits. Okay, and now from all of this, I can say the following. Okay, so the first thing I can say is that the limit as x approaches c of a constant times a function is just equal to the constant times the limit of the function, right? So b times f of x is just equal to b times L. Now, something that's kind of not explicit here, but if you think about this, what this is basically saying is that the limit as x approaches c of b times f of x is equal to b times the limit as x approaches c of f of x, right? And so I can pull that constant out of the limit, right? That's what this is basically telling you. So you can take this thing and you can pull it out here. All right. Item 2 here says that the limit as x approaches c of f of x plus or minus g of x is just equal to L plus or minus k. Okay, so the limit of the sum is equal to the sum of the limits, right? And so another item here that's not explicit, but you should recognize this, is that the limit as x approaches c of f plus g is equal to the limit as x, well, let me write it differently. The limit of f plus g is equal to the limit of f plus the limit of g, right? So I can pull the sum apart. I can take the limits separately and add them, okay? If f and g both have limits, then I can take these things and I can pull them apart. All right, the third item here says that the limit as x approaches c of f of x times g of x is equal to L times k, right? And so similar to the previous examples, the limit of f times g is equal to the limit of f times the limit of g, right? So I can separate these apart. I can find the limit of f separately, the limit of g separately, and multiply them together, right? That's what this is basically saying. All right. Item 4 here is real similar to item 3. Item 4 says the limit as x approaches c of f of x divided by g of x is equal to L divided by k. Now, I don't have it written on here, but it's very important that g of c not equal 0, right? So, that k not equal 0, right? The limit of g cannot be equal to 0. Otherwise, this would be undefined. Okay. All right. So, but otherwise, you can think of this as the limit of f over g is equal to the limit of f divided by the limit of g, right? So you can do this kind of you can bring the limit into the numerator, bring the limit into the denominator, evaluate them, and then divide them down. Okay, and then finally, this guy here, the limit as x approaches c of f of x raised to the nth power is just equal to the limit raised to the nth power. Okay, and so you can think of this like the limit of f to the n is equal to the limit of f all raised to the n, right? So you can kind of like bring the limit inside here. Okay. All right. Very good. So those two theorems in particular get you a huge range of functions. You can evaluate a whole range of functions just using those two, namely polynomials and rational functions. Let's see an example here of how to use these. So I want to evaluate the limit as x approaches 2 of 4x squared plus 2x plus 3. Okay. And so what I can do is I can use the g plus or minus f theorem to kind of break this apart, right? So 4x squared plus 2x plus 3. These are three different terms. They're separated by this addition, right? So I could break this apart. I could say the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 2x plus the limit as x approaches 2 of 3, right? So I can break it apart. Further, I can use the b times f of x, this guy here, to pull the 4 out front and to pull the 2 out front, right? So this becomes 4 times the limit as x approaches 2 of x squared plus 2 times the limit as x approaches 2 of x plus the limit as x approaches 2 of 3. So I can kind of break these things down. Right, and at this point, this is just an x to the n, this is just an x, and that's just a constant, so I can just plug in. Right, so 4 times 2 squared plus 2 times 2 plus 3 is 16 plus 4 plus 3, which is 23. Right, so this limit is equal to 23. Okay, now you can see throughout here that I used different theorems, right? I broke it apart first using the plus or minus g plus or minus f theorem, and then I pulled the 4 out front, so that's the b times f theorem, right? And then I used theorem 1 by just plugging in the values. Okay. Now this is an example of evaluating the limit of a polynomial. This is a polynomial function, right? And so it turns out that always works. What we just did always works. And what did we do? Well, we basically just plugged in c, didn't we? We plugged in the limit point into the function. We plugged it in here, we plugged it in there, and we evaluated it. Well, it turns out, and our next theorem confirms this, that anytime you have a polynomial, you can find the limit just by plugging in the limit point. So if p is a polynomial function and c is a real number, then the limit as x approaches c of the polynomial function is just the polynomial function evaluated at c. Very straightforward. And though not a proof, you can kind of look at the previous example and say, oh, just take the form of a polynomial and apply the previous two theorems to it, and you can see that what you're going to end up doing every time is just plugging in that limit point. Okay. And similarly, a rational function is the same way. And so remember, a rational function is just the ratio of two polynomials. And so you get the same basic outcome. The limit of a rational function is just the rational function evaluated at the limit point. So if r is a rational function given by r of x is equal to p of x over q of x, and c is a real number, of course, a real number such that the denominator function, the denominator polynomial q, when evaluated at c is non-zero, right? If I plug c into this, I can't get 0. If I do get 0, then all bets are off. But if q of c is not equal to 0, then the limit as x approaches c of the rational function is just the polynomial in the numerator evaluated at c divided by the polynomial in the denominator evaluated at c, right? So you plug in c, simplify, and you get the limit. Okay, let's see some examples. Let's see an example of that one in particular. Because the second theorem basically is the first theorem, but with the denominator also. So it's like the first theorem twice. Let's evaluate this limit. The limit as x approaches 1 of x squared plus x plus 2 divided by x plus 1. Okay, let's see what happens here. And so what we need to really confirm, we see this as a rational function. What we need to confirm is that this denominator is not equal to 0 at the limit point. So if I plug in a 1 there, what do I get? Well, I get 1 plus 1, 2, so not a problem. And so that means that the limit of that whole thing as x approaches 1 is just 1 squared plus 1 plus 2 divided by 1 plus 1. And so I get 4 over 2 or 2. Very good. All right. And so we now can evaluate the limits of, we can identify the limit of any polynomial or any rational function, right? Assume, so long as the limit point that we're looking at does not create an issue in the denominator of the rational function. All right, so let's keep going. We're making tremendous headway. We've just carved off a huge swath of everyday functions that are now, we can identify the limit of. Great. Let's take a look at the case when n is a positive integer and we're dealing with square roots or roots. So let's let n be a positive integer. Then the limit as x approaches c of the nth root of x, right? So like think of like the square root of x, the cube root of x, fourth root of x, etc. This is equal to the nth root of c. So again, we can just plug in c into this limit, but there are a few hooks in it, right? Because we're dealing with square roots, and so we always have to be cognizant of square roots of negative numbers or fourth roots of negative numbers, basically square roots of negative numbers. It all kind of boils down to that. So this works only if n is odd, right? So if I'm looking at like the cube root of x or the fifth root of x, that's okay. In that case, x can be anything, any real number. But if n is even, right, if n is like the square root of x, then my c cannot be a negative number, right? Cannot be a negative. This should be greater than or equal to 0. C cannot be a negative number. And basically what this is guarding against is trying to identify the limit as x approaches -1 of the square root of x. Right, this right here, if I try to use this theorem, would say that the limit is equal to the square root of -1, which is not a real number, right? So square root of -1 is equal to I, which is not a real number, right? And so that's the only problem there. It's just that this is not a real number, and this is calculus on real numbers, and so we can't identify the limit if the limit is an imaginary number or a number with a complex part. Okay, right? But otherwise it's fine, right? And so let's see an example or two of this just to make sure we're clear. Let's evaluate the limit as x approaches 27 of the cube root of x. So nice conspicuous limit point 27 there. So the limit as x approaches 27 of the cube root of x. Well, in this case, n is odd. So I don't really care what my limit point is. I can just plug it in, right? And I get the cube root of 27, which turns out to be 3. All right, so let's take a look here. The next example, evaluate the limit. Now here the limit is the limit as x approaches -2 of the square root of x. Okay, so my limit point is a negative number, right? And this is technically 2, so that's even, right? And so the theorem up above said that if n is even, then c needs to be greater than 0, right? So in this case, n is even, but c is less than 0, right? And so I have a problem. I can't apply the theorem, can I? No. Right? And so why can't I apply the theorem? What's the problem here? Well, this would be the square root of -2, which would be like the square root of 2 times the square root of -1, which doesn't work, right? And beyond that, like you can see, the function isn't even defined over here at x equals 2, -2, right? So -2 would be over here. The function isn't even defined there, right? So The square root of x is not defined for x less than 0. Therefore, the limit as x approaches negative 2 of the square root of x does not exist. Okay, very good. So hopefully that's clear. We're just kind of, we got to keep things real when we're dealing with limits. Okay, very good. So the next theorem breaks, so we've talked about polynomials, we've talked about rational functions, we've talked about constant functions, and all of the constituent parts of any of those types of functions. So now what we want to talk about are composition of functions. So this theorem says if f and g are functions such that the limit of g, such that the limit as x approaches c of g of x is equal to L, and the limit as x approaches L of f of x is equal to f of L, then the limit as x approaches c of f composed of g is equal to f of the limit as x approaches c of g of x, which is equal to f of L. Right, so basically, given the right conditions on the limits here, you can move the limit inside of f, right? So you can see you move the limit inside of f here. Okay, and so if the limit of the interior function, that's the g, is equal to L, and the limit of the exterior function, f of c, and this is a typo, as x approaches L, then we may move the limit into the composition. Okay, and so this is all going to be this may seem very wordy and difficult, right? But the idea here is that if we know the limit of the interior function is equal to L, and we know that the limit of the exterior function as we approach L, then we can do this maneuver. Okay, let's see an example here. Let's see an example. This is something that becomes a lot clearer when you take a look at an example. So let's say we want to evaluate the limit as x approaches 0 of the square root of x squared plus 4. And so you've got these two parts. You've got this inside part here, which is the polynomial x squared plus 4, and you've got this outside part here, which is the square root. So what we'd want to say is that this is equal to the square root of the limit, right? But is it? Let's see. So the first thing we do is we take a look at that inside and we say the limit as x approaches 0 of x squared plus 4. Well, that's just a polynomial, so plug it in. 0 squared plus 4 is equal to 4, right? So the limit of the inside at 0 is 4. Now, what then we can then do is we can say, okay, then let's take that limit and use that to evaluate the exterior function, right? So the limit as x approaches 4 of the square root of x is equal to 2. Right? So effectively what we've done is we've moved the square root outside. So we've kind of pulled it out, or I guess maybe a better way to say it is we pull the limit inside. Okay. All right, here's another example. Let's evaluate the limit as x approaches 10 of the square root of 2x plus 5. Okay, so the limit as x approaches 10 of the square root of 2x plus 5, that's equal to the square root of the limit as x approaches 10 of 2x plus 5, which is equal to the square root of 2 times 10 plus 5. Right, so we've kind of pulled this piece here inside the radical, as you can see here. Right, and so you get 2 times 10 is 20, plus 5 is 25, and then the square root of 25 is 5. And so that's the answer. And so this is all very intuitive, actually. If you think about it, in this case, you're just sort of evaluating the function. You're just, again, still just kind of plugging in that value, right? But technically speaking, you do have to make sure that these conditions are true. It is possible to construct an example where those conditions don't hold, and therefore this doesn't work. Okay, very good. The next theorem is a laundry list theorem, total laundry list theorem. We're not going to prove any of these, but we will see examples later that we'll look at in more detail, specifically when we get into continuity. But basically, this is going to wrap in all of the trig functions. And so the trig functions are special kinds of functions that you've seen if you've taken trigonometry or pre-calculus. But one of the properties of trig functions is that they have this continuity thing that we'll get into next lecture. But the continuity thing allows us to just plug in the limit points. So let's let C be a real number in the domain of the given trigonometric function. Then here we go. The limit as x approaches C of sine is just sine of C. The limit as x approaches C of cosine is just cosine of C. The limit of tangent is just tangent of C, cotangent of C, secant, cosecant. So basically all 6 trigonometric functions, you can just evaluate straightforward, right? You just plug in the limit point and you get the limit, right? And so that's, so the only caveat here is that C has to be in the domain of the trig function, okay? And so that's the only caveat. So sometimes, for example, if you recall your tangent and your cotangent, they'll have certain values where they're undefined, and so you obviously can't evaluate the limits at those values. Same with secant and cosecant. Sine and cosine work everywhere, but these four here, you have to be a little bit careful of the domain, but most places it's fine. And then two more pieces to this theorem. The limit as x approaches C of a raised to the x power is just a raised to the c power. Okay, so that's nice. And then the natural log. The limit as x approaches C of the natural log of x is equal to the natural log of C. Laundry list theorem. Again, you could prove these if you want to. When you get to real analysis, you'll prove them, or some of them. Some of them are very repetitious. You prove one, you kind of get the rest of them. But we won't prove them here. This is Calc 1, so our interest is just like, what are these limits, and then let's be able to use them. Let's do some examples here. Okay, so the first example says, let's evaluate the limit as x approaches pi of x times the cosine of x. Okay, so here's a case where we can take two functions and split them apart. So you got the x and you got the cosine of x. So the limit as x approaches pi of x times cosine of x is just equal to the limit as x approaches pi of x times the limit as x approaches pi of cosine of x. We know this, so we get pi times cosine of pi, pi times -1, so negative pi. Okay, so again, just using the theorem to break this apart. This was from basically theorem 1, and this was from the previous theorem. So we get pi. It was basically evaluating these. The next example, let's evaluate the limit as x approaches e of the natural log of x cubed. So e, remember, this is the base of the natural log. And so what can we do? Well, the limit as x approaches e of the natural log of x cubed. Now, if you remember your natural logs, if I have the natural log of x to the n, that's equal to n times the natural log of x, right? And so that's what we're doing here. So basically this 3 comes down front, right? So you get the limit as x approaches e of ln x cubed is equal to the limit as x approaches e of 3 times the natural log of x. Now, this is just a constant, and that we just saw in the previous theorem. So we can pull the constant out front if we want, and we get 3 times the limit as x approaches e of the natural log of x, and we can plug those values in, 3 and 1, and we get 3. All right, straightforward. Here's an example where we're combining a trig function with like a polynomial in the denominator. And so the limit as x approaches 0 of tangent of x divided by x squared plus 1. Okay, and so we'll kind of treat these two separately. We'll treat the numerator first and then separately the denominator. And so that's what we see here. We move the limit into the numerator and into the denominator, and we have the limit as x approaches 0 of tangent of x divided by the limit as x approaches 0 of the polynomial x squared plus 1. And we know that we can just evaluate these, right? 0 is in the domain of the tangent function, and the polynomial is defined everywhere. And so we get tangent of 0 over 0 squared plus 1. So 0 over 0 plus 1. So just 0. All right. And here is the last example. And so here we want to evaluate the limit as x approaches 0 of the cosine of sine of x. All right, so you got kind of a composition here. Right, and so basically all we've done is just we're going to plug this into the x, and we'll get a number there, and then you've got a constant function basically. So the limit as x approaches 0 of cosine of sine of x is equal to the limit as x approaches 0 of cosine of sine of 0, and you get cosine of 0, and you get 1. Okay, very good. All right, so that'll be the end of part A. Now in part B, we'll continue with evaluating limits analytically, and we'll look at a range of additional theorems that can be used to evaluate limits. So we'll see you then. Take care.